Hello friends, welcome. Today I am going to talk about a topic which is called FDD versus TDD. This is part of the concept video that I recently started to explain complex terminologies to the common man so that the public discourse which happens using these terminologies can be easily understood. And there are implications which spill over in other terminologies, by using these terminologies. So those also you can understand. So since we have limited time in this video, so without wasting any further time, let's go to the concept diagram. So this is the actual representation of an FDD spectrum. What is FDD? It's called Frequency Division Duplex. Now the term Frequency Division Duplex is basically represented by this diagram where two different frequency blocks are used to transmit signal from one point to another. So this is the point. Let's assume that this is the point where a base station is located. So the base station is going to transmit using the top part of the frequency block to the another base station which is going to be located here. So this base station is going to be receiving, which is the second base station which is located here, and this is transmitting, and the lane that it is going to use is going to be this lane. Similarly, the bottom part is going to be used for transmitting by the second base station and being received by the first base station. Now, if you see here, this block of spectrum, which is coupled together with this block, is segmented into slices. These are called channels. Now, one particular slice, let's say it is of a particular width. Let's assume that it is 10 megahertz. Now, when you make assignment to the operators, you can't assign 10 megahertz here and 5 megahertz here. You have to assign it equally. So, if you give 10 megahertz here, then you have to give 10 megahertz here also. That's why this 2 into 10 megahertz. Now, you might have already heard about this term 2 into 10. From where this 2 into 10 is coming is because of this reason, because the way the assignment is made for FDD spectrum. So here what happens is that the amount of bandwidth which is available in the transmit path is always going to be equal to the bandwidth at the receive path, right? So transmit and receive path have equal capability from the point of view of using bandwidth. That is why it is 2 into 10. Now friends, in case of TDD, it is quite different. In TDD, both these blocks, because this bottom part is the TDD spectrum band structure. Now, both these blocks, which are separated out by a duplex spacing, which is nothing but a no man's land, nothing is being used here. This spectrum portion is free. And you need to have a guard band here, otherwise this is not going to work, and I'll explain to you why. Here what is happening in TDD, they are clubbed together in single block. So difference between FDD and CDD is, in FDD you have got two different blocks, one top and one bottom separated by a duplex spacing, and in TDD both of them are clubbed together. Now in FDD already you know that both these are used separately and a continuous manner for transmission, means the transmission is happening on the top path on a continuous basis and the bottom part in this direction on a continuous basis. Whereas in case of TDD it is different. The transmission happens in one direction using the full block of spectrum, and the receiver is just listening. It is not transmitting anything. For example, the base station here is just listening mode when this particular base station is transmitting. Now, once the transmission is finished from this particular side of the base station, then this particular base station will start transmitting, and this is going to start receiving. It's almost similar to the following analogy. Let me just go to this diagram. If you look at this diagram, which is TDD spectrum band analogy, which is kind of giving you an analogy of a road, of a tunnel, where only one single lane is there. Means these cars are waiting in one direction for the cars from the other side to, just like you see the car is coming here, the cars are coming here. So once the cars on the other side they will wait till the time there is a complete arrival happens from the other side, or there is a block of time for which the assignment is made for the other side cars to travel in this direction. Once that is completed, then these cars are going to flow in the tunnel. Means there is not simultaneous transmission happening between or simultaneous traffic flow happening within the tunnel for the traffic. It's almost like the Jammu and Kashmir Jawahar tunnel. When I visited Jammu and Kashmir around 20-30 years back, at that time the tunnel was only opened in one direction at a time. Reverse direction, it was not open simultaneously, otherwise there will be collision. So let the traffic flow in one direction for a certain duration of time, and then after that This is closed for the traffic transmission from the other direction, and the traffic start flow from this direction. That exactly happens in case of a TDD spectrum. The transmission does not happen simultaneously. That is why when the assignment is made, the full block of spectrum, 10 megahertz on top and 10 megahertz on bottom, is assigned together in 20 megahertz. So there is no 2 into 20 megahertz here. Now friends, if you aggregate spectrum of FDD and TDD to determine how much spectrum has been sold or acquired by the operator, it is not proper to add these two blocks of spectrum, without dividing this 20 megahertz by 2. Because if you are going to add, say 10 megahertz, because 2 into 10 megahertz nobody writes, it's a 10 megahertz of FDD spectrum, and if you add 20 megahertz on 10 megahertz, it will become 30. Now this is going to give a wrong representation, because in case of FDD spectrum, 10 means 20, but you never add like that. You assume that the other part of the spectrum is tagged along with the 10 megahertz, and then you add the 20 megahertz on top of it. This is not the right way of adding spectrum. You have to make sure that when you are making aggregation of these two bands to represent how much spectrum an operator has, you proportionately reduce this number. Now there could be one way to reduce this number, could be by divided by 2. But that also may not be accurate representation. Because what happens in case of TDD, sometimes, in case of TDD, the transmission in the forward direction and the reverse direction may not be same amount of resources may not be assigned. Means the uplink may be smaller in chunk. The resources for the uplink will be smaller in chunk compared to the downlink. So you may be using more resources in the downlink, because the downlink speeds are generally higher in case of internet application, because you download more than uplink. So let's say if you have 20 megahertz, out of 20 megahertz you may be using 15 megahertz worth spectrum or resources for downloading, and maybe 5 megahertz for uploading. So then the aggregation may not give you an accurate representation. So you should be aware of this fact. That's why I'm emphasizing on this particular point. The second point to note here is that the TDD spectrum blocks that I have used here are shown adjacent with each other. Now this adjacent blocks of spectrum which are laid out adjacent to each other is laced with a very important assumption. What is the assumption? That the spectrum blocks needs coordination between the operators to work adjacent to each other. What I mean by coordination? Basically what I mean is that this particular block, which is I marked with an amber color, is for an operator A, and the green one is for operator B. Now both the operators will have two different base stations. Now let's say the top part, the operator A, is transmitting, and the bottom part of the operator is receiving. Let's assume that, okay, for the time being, because there are two different blocks of spectrum for two different operators, 20 megahertz each. So the top is transmitting, the bottom is receiving. What will happen? There could be some spillover from this particular spectrum block to this block. So when this particular BTS is transmitting using the top part of the spectrum block, and this particular BTS for a second operator which is receiving spectrum from here, then there could be chances that there will be some spillover of RF signal from this particular spectrum block to this spectrum, choking this receiver. So both of them have to transmit simultaneously and receive simultaneously to prevent that choking to happen, because you can't have an RF spectrum where no spillovers adjacent in other bands. It is practically impossible to have a situation with filter with such sharp cutoff to prevent spillover of RF spectrum emanating out of the band. It's always going to be there. So since the transmission is at very, very high power, therefore the spillover might happen into the receiver of the other spectrum band, other operator, and it will create problems. So they have to synchronize with each other, which is not in this particular case, because here both of them are transmitting and here both of them are receiving, so there is no problem, right? So even if there is a spillover here, because it is transmitting, there is no choking. So in FDD, the frequency spectrum blocks can be adjacent with each other with no coordination requirement. See, there is no coordination requirement here, whereas in this particular case, coordination is must between the telecom operators for them to use these spectrum blocks adjacent with each other. Otherwise, there needs to be a guard band here. Means you have to basically take this out, right? So I have to remove this, and there has to be guard band here, and then only these two spectrum blocks can be used in an uncoordinated manner. Otherwise, you can't. So this is the important limitation of a TDD spectrum, right? So you have to understand this, that TDD may end up wasting spectrum if you are going to use in an uncoordinated manner. You have to coordinate, which basically means that whatever scheme of download and upload this particular operator is using, the same download and upload is going to be used by this operator also. You have no other choice. Let's say if it is using 2:1, means, if you have 20 megahertz spectrum, that the uplink part, the downlink is going to be 2 times the uplink. Then this particular operator also has to use the same particular approach. You can't have a different approach, otherwise you end up wasting a lot of spectrum. So that's what the difference between a TDD and an FDD band structure is. FDD has got, now the TDD has got this limitation, FDD doesn't have this limitation. Now let's understand that why low frequency band are not being structured in a TDD fashion. Why only high frequency bands? You might have noticed that 2.3 gigahertz band, 3.5 gigahertz band, 26 gigahertz band, every band are TDD nature, whereas the FDD band, basically if you look at the sub gigahertz band like 700, 800, 900, 2100, 1800, they are FDD bands, they are not TDD bands. Now let me tell you the reason why. The reason that the low frequency band are FDD and high frequency bands are TDD is because of this particular problem. Now let's go to this chart first and then we'll come back to this chart. Now if you see the grid structure of a base station, may look something like this. Means, let's say if you have an operation, you may have different base stations located at different parts of the network. Now what happens is that because all these base stations will be transmitting simultaneously and receiving simultaneously, as I told you, it has to be synchronized with each other. So once this base station is, let's say this is a base station which is transmitting, right? Now let's say it transmits for a duration of 20 milliseconds. That's the frame structure of transmission. Now after the 20 millisecond is over, all these base stations will be in the receiving mode, right? Because everybody will be transmitting for 20 milliseconds, and then as soon as the transmission is over, it will be in the receiving mode. Now the problem is that as soon as it becomes in receiving mode, let's assume that the signal from this base station is getting transmitted and it is continuously in the air. It does not die off. It does not attenuate. It keeps transmitting and it comes to this particular base station also. It reaches this base station. Now this distance can be as high as 20 kilometers, 30 kilometers, 40 kilometers, right? Now, if it is going to be such long distance, and it can be very, very high also, I'll explain to you why it can be hundreds of kilometers also. Let's now assume that it is for a sizable number. You know that signal will take some time to transmit in free space, which is the velocity of light. Now, this base station has to assume that the signal from this particular base station, which is on the air, right? Because when it cuts off after 20 milliseconds, it will cut off, but still there will be signal in the air. So this base station has to assume that this signal which is in the air should not block its receiver, because as soon as it goes in the receiving mode, because everything will be synchronized using a GPS clock, this transmission which is happening over the air, the signal which is remnants over the air, still in the air, can come and block its receiver, because as soon as you open up the receiver, the transmission which is already in the air can block the receiver. So you have to take that factor into consideration so as to prevent that blockage. The receiver will get choked if signal is still in the air, transmitting in this direction and entering the receiver here, because when it opens up the receiver, that receiver will start receiving the signal which is already in the air, because 20 millisecond, after 20 millisecond, as soon as you stop and start receiving, but you cannot stop the signals which are already in the air because they are transmitting. So this aspect of TDD gets further aggravated by an atmospheric phenomena called ducting. So this is being shown here. Now what happens is that in winters, the atmospheres basically form a duct. Now let's say this particular base station is there. Now every base station will be throwing some signals for the user to receive services. Now what will happen is that if this base station is throwing signals, and instead of it is receiving the user here and there, some of the signals actually lands up into the atmospheric duct. And once it gets into the atmospheric duct, it can travel hundreds of kilometers. Because the signal does not die out, it gets locked into this duct, means it will travel like this. And it might reach a base station which is quite far away, maybe 400 kilometers, 500 kilometers. So that base station will not be expecting a signal which is coming out. Let's say as you are having a base station in Delhi, and let's say there is another base station in somewhere Kota or somewhere in between. That base station will not be configured for for the signals to remain in air for 200 kilometers or 300 kilometers or 500 kilometers, right? It will basically make the system very, very inefficient. So this problem makes the TDD system very inefficient if you are going to use it for low frequency band. Because in case of low frequency band, what happens is that because you know that low frequency band travels much farther because of the natural propagation characteristics of low frequency band at the low frequency spectrum band, the sub-gigahertz band has got better reach and better coverage. We all know that. That's why the value of the low frequency band is very, very high. Right? Because you can put less number of base stations to cover a larger geography. Now, if you are going to use a low frequency band in TDD, then this phenomena of the signals reaching out to nearby base station is going to be much higher. So you have to block this base station's receiver, right? Even though this particular base station has transmitted for 20 milliseconds, but you have to extend the time for another, let's say 3 milliseconds or 4 milliseconds, depending upon the time the signals are already in the air. So as to prevent those signals getting into the receiver, you have to lock that particular time. You can't do anything within that particular time period where the signal is already in the air. So the chances of those signals remaining in the air is much higher in the low frequency band in the higher frequency band, because higher frequency band can attenuate much faster. So that is why the low frequency bands are not used for TDD. You will always find that the low frequency bands are all used in FDD bands, FDD structure. They are not used in TDD because of this particular reason. Okay. Now, going forward, how these inflexibility, like what I'm basically trying to tell you, that you can't use a particular band structure in a particular spectrum band, but you can use a particular band structure in a different spectrum band. How these limitations can be overcome? That is what 6G is all about, right? So one of the aspects of 6G is to overcome this limitation, which basically means if you are able to create a technology which will have such sharp cutoff filter to prevent these spillovers from happening from this particular spectrum band when it is transmitting to this particular spectrum band, then you can enhance the flexibility of the spectrum and do whatever you want, right? And if you can do simultaneous transmission and receival, let's say if you are able to have a TDD spectrum structured in such a way that you don't have to follow this particular approach, what I told you, wait till the other side completely, the traffic from the other side stops, and the lane is open for you, means there is no simultaneous transmission and reception happening here. The roads are not opened simultaneously. It's not a double lane structure. So what the 6G is trying to do is, because of this particular issue of inflexibility of a particular spectrum band and a wastage of spectrum because of duplex spacing and the lack and the need for synchronization, those things can be worked upon by enhancing the filter cutoff capability and modulating the transmitter and receiver design such that those kind of interferences that may happen when you are doing simultaneous transmission can be mitigated. And if you do that, imagine that you don't require any spectrum planning. Because what is the problem with today is that when you do a duplex spacing, then a band structure decide what kind of equipment that is going to be embedded in the mobile phone. Even a small change in duplex spacing impacts your mobile phone significantly. Let's say if US is using a certain band structure for a particular spectrum band, the low frequency band, and you do not have that band structure and you are using a different band structure with a different duplex spacing, you cannot work those equipment here in India. A small change impacts the equipment capability significantly. So you can overcome those and make the frequency planning much more easy, right? When you prevent these limitations and make the filter cutoff design so sharp that these kind of spillovers does not impact the antennas, and does not block, sorry, it does not impact the receivers on the same base stations, or your competitor's base station who is using and transmitting at the same location. So this is in nutshell the summary of this particular presentation. So what I am going to summarize in the last chart, which says that FDD structure is utilized for low frequency band, as I explained to you the reason why. TDD is utilized for high spectrum band. FDD is less flexible, as I told you that a small change in duplex spacing can have a huge impact of the operator's ability to use a particular kind of equipment or the phone, because there will be slight change in duplex spacing will change the structure of the band totally, you can't use. But TDD is more flexible because you can assign as much spectrum as possible in whatever way. There is no duplex spacing requirement. And this can be further enhanced if you are basically going to improve the need to prevent the operators to coordinate by doing simultaneous transmission on a TDD band from both the sides, by enhancing the equipment in such a way that those equipment become capable of doing that. But today they are not capable of doing that because of the interference and the filter limitation, which I explained to you. So these are the opportunity of enhancing spectrum capability in near future with 6G, with artificial intelligence, machine learning, and all those capabilities will basically help enhance these capability. Empower the operators to use these features and further enhance the spectrum, the current spectrum ability to carry more traffic with much more flexibility. And you don't require guard bands, and it will prevent wastage of spectrum. So friends, I hope that you probably have understood what these concepts are, and I think you will be much more capable to understand it in near future in public discourse, and the limitation of a particular band structure for a particular kind of network architecture, and why a particular network architecture or if FDD band is used in low frequency band, why TDD is used in high frequency band, and what kind of limitations are there, and what 6G will be able to do in near future, and how it will enhance spectrum planning, and it will simplify spectrum planning. It will enhance the efficiency of spectrum going forward significantly, right? Thank you for your time, and I will hope to see you in the next concept video in near future. Thank you very much.